Hi everyone. In the last video, I ran some of my sample programs side by side on my Raspberry Pi 4 Model B, as well as a new development board that I've added, which is the Google Coral Edge TPU dev board. In this video, I want to show the running of my sample OpenCV application, which I've used in previous programs on other boards. I want to show it here running on the Coral dev board. In order to do that, I compiled ISPC on the dev board, on the Coral dev board, and so I can take advantage of ISPC SIMD Parallelism. I can vectorize a lot of the code and be able to do some of the OpenCV some of the things that I wanted to do in my OpenCV application. So what you see on the screen is the desktop of the Coral board. So just to kind of get a sense of what this board has, it's running Linux kernel 4.1498. It has only 1 GB of RAM, and actually the model that I have only has 1 GB of RAM. What I'm seeing is that there is a 4 GB version available now. So I don't think it was available the other day when I was recording my other video, but now that I look at the website for it, I can see that there is both a 1 or 4 GB version of it available. It still is comes with 8 GB of eMMC, but that's too small for what I need. So I am booting the Mendel Linux on version 4.0, which is the code name Day. Day stands for the letter D, I think, in the release ordering. So this board has a micro SD slot. I have a 32 GB micro SD slot, and I've built the Mendel Linux 4.0 for the Coral dev board, and I'm booting it off of that. So I'm actually happy to see that the 4 GB version is available. I might upgrade to that at some point, but since the one that I have is limited to 1 gig, I had to make some modifications in the sample program in the OpenCV sample program in order to be able to run it on this board. Fortunately, I am able to take advantage of ISPC vectorization and get some SIMD parallelism there. But one of the other things that I wanted to point out is that when I was running the OpenCV application, so actually any time I ran a graphical program, in this case, my OpenCV application is using OpenGL, and it's using IMGUI in order to render these captured images from that the program captures from OpenCV, captures from the camera using OpenCV. Anyways, when I was running that, the screen would go dark, and then I wouldn't be able to recover it. There was no way for me to turn it back on. It seems like the screensaver was coming out, or screen was being blank. So what I had to do is I had to install a couple of packages, especially this one, X11 Xserver utils. This one allowed me to use the xset command to turn turn the screen blanking off and power save off, I guess, so that the screen doesn't go dark. this other package libxext16 is supposed to provide DPMS as well, but even though I installed it, I get the message that the server does not have extension for -DPMS option. But it's sufficient to run the exec s space off and exec s no space no blank. Those two commands are good enough for me to be able to run the graphical application and not have the screen go blank. This doesn't happen when I just open a terminal. It happens when I run some sort of a GUI application. So this is an issue I was experiencing with Mendel Linux 4.0, which I built for booting on the SD card. So I wanted to point that out. With this enabled, I can just now run the OpenCV application and be able to, let it run for a while. In any case, as I said, my my Coral dev board has only 1 GB of RAM available. At the moment, I'm not running any swap file. And again, the version of Mendel is Mendel Linux 4 day. And that's the code name. And this is a derivative, or this is the lineage for this goes back to, I think, Debian Buster 10, which is similar to Raspberry Pi 4, Model B. Anyways, I'm going to close this. One more thing I'll type here is the df-h command. And as you can see, I have 32 gigabytes SD card. I've used 9 gigs of it in order to be able to do this, run this demo. And I still have 21 gig free. So I'm going to put this away. In this terminal window here, I'm running top. So while I run my time exposure application, which is an OpenCV application that does typically it does a 10-minute time exposure. But to do a 10-minute time exposure at 10 frames per second, that requires about 6,000 frames. So this Coral dev board, mine, the 1 GB model, just doesn't have enough RAM to do that for me. I keep all of that in RAM, so I don't write it to the SD card at all. I want to keep it in memory, at least for now. So I had to modify the settings for my program so that it would only do a 1-minute exposure. So on the Coral dev board, I'm doing a 1-minute exposure. So it takes, but even with the 1-minute exposure, as you can see, the Coral dev board is unable to keep up with my targeted 10 frames per second. Normally I do, like I said, 10 frames per second for 10 minutes. That's about 6,000 frames that make up the 10-minute exposure. But I cannot keep that target rate, capture rate. So what I'm seeing is about 5 frames per second, a little bit more. So at this rate, I've told my program to do a 1-minute time exposure, but because the frame rate is not at the desired 10 frames per second, it's about half. It's actually going to take about 2 minutes to do the same amount of time exposure. So in reality, I'm doing a 2-minute time exposure at the 5 frames per second rate. Anyways, so with that explanation, what you see in top the program is limiting itself to about a quarter of the available memory. So far it's been running for a while, and it's pegging at 28.4. It doesn't exceed that. But as you can see, the CPU, it's just using the CPU like heavily. So I'll do a comparison with the other platforms, and you'll see the other platforms are able to run at a still leave some bandwidth available on the CPU. But in any case, what you see is in this picture here, on the right is the live picture, on the left is the 10-minute time exposure, and what I'm doing at the bottom is the FFT of the grayscale version of the colored live picture. And on the left bottom, what you'll see is the FFT of the 10-minute exposure, which is the picture above it. All of the results that I'm seeing right now are taking advantage of ISPC, Intel's SPMD Program Compiler, running on the ARM Cortex-A53 cores, using all 4 cores for ISPC vectorization, and doing it in parallel on 4 cores. So that's the best so far that I can get. This is better than if I did it in C++ or even in OpenCL. I have tried both of those, and with ISPC I get the best results on this platform. Again, this is not really taking advantage of the TPU. You wouldn't buy this board to do this sort of thing. I think you would buy it to take advantage of its TPU, the machine learning accelerator that is built into it. But if your application it has other things to do, it's good to have some benchmarks on how the CPU and the GPU perform. So here, this is a good sample program for me to kind of gauge the capabilities of this board. Now, in this scene, you see the Raspberry Pi 4, and as you can see, the Raspberry Pi 4 has no problem keeping up the 10 frames per second and still do the same rendering of the FFT visualization, as well as doing the capturing of the frames and converting them to grayscale and performing the time exposure. And on the left, as you can see in the top, in the output of the top program, CV Timex is using about 47% of the memory. So about less than half. That's 2 gigs. That's how much memory is needed to keep 10 minutes of time exposure frames in memory. So I don't have to write it to disk. It is using a lot of CPU. It's more than 100%, but all of that is happening on really just the ISPC SIMD vectorization is done in parallel on all 4 cores of the Raspberry Pi and all of these platforms. But the rest of the program is single-threaded. The rendering is done on the main thread. Capturing from OpenCV, capturing from the camera using OpenCV is done on the main thread. But converting the color image to grayscale and then doing the 10-minute time exposure is done using ISPC as much as possible. And that's done in parallel as well on all cores. But the OpenCV interface and the OpenGL interface, IMGUI rendering, is all single on the main thread. In the next screen, what you see is the Jetson Nano development kit. And as you can see here, also the Jetson Nano is able to keep up the target at 10 frames per second, and it's rendering the same output, and it's also limiting itself to in the output of the top program. CV Timex is the name of the program. It is showing at about 46%, 47% of the memory, and the CPU is underutilized. I mean, it's not at 100% utilization, it's 66%. And then comparing it to the NanoPi M4, the friendly NanoPi M4, similar results. The NanoPi is able to keep up with about 10 frames per second. Sometimes it has a glitch and it does more, even though I've requested it to be 10. It's not really limiting itself by the 10 frames that I'm targeting. So it turns out apparently that if it had more bandwidth, it could give me more frames per second. But I try to limit it to 10 so that I have that's the formula that I have. But obviously here it's running sometimes at 11.11 frames per second. But in terms of memory, it is keeping itself limited to half the memory, but it's using the CPU quite a bit. So here at the bottom half of the screen, what you're seeing is the Coral dev board, and on top what you're seeing is the Raspberry Pi. So you can see it side by side here. 10 frames per second for the Raspberry Pi, 5.26 frames per second for the Coral dev board. Here you can see side by side, or sort of with the Jetson Nano dev kit on top. On the top half of the screen, you can see that the Coral Edge dev board is capable, but it's not running at full 10 frames per second. And here is the side by side with the NanoPi M4. Some of the screen might not be visible, but the key thing is that they're running the program, and that the frames per second is the number that I try to maintain at 10 frames per second. Let's see. Now, what I want to do now is do a comparison between this is ISPC. I'll just stop the video and then run it with C++, so you can kind of see the difference, and then do the same with OpenCL on the GPU, on the Vivante GPU. And those are the two other results that I can share. I'll be right back. Okay, so I wanted to switch from what I thought was ISPC and compare it to C++, but it turns out that the earlier setting I had selected was to do the computation using C++. So the results you saw for the Coral Edge TPU dev board were actually single threaded on the CPU, and there were about 700 milliseconds for the computation, and by that I mean the computation of modifying the image so that it goes from color to grayscale, and then I do the time exposure all the way to the point where I'm about to do the FFT using the OpenCV FFT function. So the OpenCV FFT function is always done in using OpenCV, but the conversion of the image and the time exposure, it was being done with C++. As you can see, the C++ checkbox is what I had checked. So I'm going to switch to ISPC, but I wanted to point out that, again, I opened a new terminal, I set the xset s off and xset s no blank, and then I ran my program again. And that's when I noticed that I had the wrong settings. I thought, anyways, so I'm going to switch, and here I'm going to select ISPC. So what we'll see now are the results for ISPC. So here I'm going to put this over here so that we can kind of get a sense of that. While that's collecting some data, we can switch to this side-by-side view and kind of see the comparison. So if you take a look here with ISPC, the time exposure computation is almost half the time. So doing SIMD parallelism, it allows me to get a lot better performance out of that stage of the program. And it looks like it affects the frames per second a little bit more. So because there's more CPU bandwidth available, the program can achieve better, a little bit better frames per second rates. So that's significant. I mean, it's not the targeted 10 frames per second, but it's about as best as I'm able to get at the moment. So this is the best results, because this is for me, because this is with actually ISPC SIMD vectorization done on multiple CPU cores using ISPC tasks. About half the time it takes compared to doing it on the CPU in C++. So I'm going to stop one more time and then run it next with the OpenCL on the Vivante GPU. Okay, now I've opened a new terminal again, and this time I've set xset space s space no blank followed by xset space s space off. I'm not sure whether this order matters or not, but sometimes I think it depends on the order I issue these. Sometimes I still get the screen goes dark, so maybe this is the right order, because when I tried it in the other order, I did see it go off. So let's see. Over time, I'll figure out which one works. But for now, I've set it to no blank first and then off. So I think this turns off power saving for the terminal. And I've relaunched my application. So now I'm going to switch to OpenCL and start capturing. And what I was going to point out is that on the Coral dev board, I have two OpenCL platforms. One is the POCL, which is uses pthreads to run OpenCL kernels on the CPU. And I also have the Vivante GPU, which supports OpenCL. The way I've ordered them, the Vivante should come up as the first platform. So the result we're seeing is it should be with Vivante, but as you can see, the results are not as good as ISPC SIMD vectorization. even though it's being done in parallel on the GPU, the amount of data movement that has to happen in order to move the data, move the frames down to the GPU and do the time exposure computation and then bring the results back up is just really defeats the purpose. It turns out even though I have a good GPU here, and maybe for some other applications it's great to have it, for this particular sample application it's not the best platform. And anyways, so here I'm going to stop and then switch back to ISPC one more time before wrapping up. Okay, so I've relaunched the application and now I'm going to switch to ISPC and start capturing, and then just let that go, and then we can compare, for example, side by side with the Raspberry Pi as soon as it prints a line, for example. So one of the other things that I had noted in the previous video is that ISPC SIMD vectorization with tasks, with ISPC tasks, doing them on all cores, is a lot more effective on the Coral dev board than on the Raspberry Pi. For example, if I compare the time exposure time, although the Cortex-A53 cores that are available on the Coral Edge TPU dev board are not as strong as the Cortex-A72s that are on the Raspberry Pi. It's ISPC neon vectorization is more effective on the Coral dev board. The time exposure computation is done in 233 milliseconds, less than 270, less than 300 milliseconds, whereas on the Raspberry Pi, ISPC vectorization for the same algorithm, same code, same C code, same C++ code, just compiled on the Raspberry Pi, it takes a lot longer. It's in the like 500 millisecond range versus 200 millisecond range. So comparing that to the Jetson Nano, this time exposure algorithm computation is about the same. It's in the 200, low 300 numbers, but on the Coral dev board, it's doing pretty well and good results there. And same thing comparing with the NanoPi. NanoPi is sort of like 300, more in the 300 range, sometimes mid 300 millisecond range, whereas the Coral board is about mid to high 200. Sometimes it goes into the 300, mid 300 range milliseconds. So that's another observation. I think that's about it. These are the kind of comparisons that I wanted to make, and hopefully this is useful. And I'll see you in the next video. Thanks for watching.